In this lecture, we're going to be talking about variable and model selection methods. And to begin with, we need to talk about the idea of active and inactive terms. We'll start with thinking about all of our predictor variables in our data set represented by the matrix X. And we're going to divide up the variables in our predictor set into two parts. The predictors XA, predictor variables, some predictor variables go into the partition, the set XA. Those represent active terms. And other variables that are in our data set but do not enter the mean function are the predictors in the partition XI for the inactive terms. And the distinction between active and inactive terms is that the active terms, those predictors, are really part of the data generating process for the mean or the variance function. And the inactive terms are in our data set, but they really don't contribute to generating the mean function. And so when I write this expression here for the mean function of y given x, you'll notice the way I've written it is that all of the variables are part of it, except for the inactive terms, the beta generating coefficients are actually 0, which wipes out their contribution. And the problem that we have as statisticians is figuring out which predictors are active and which ones are inactive. Here's a little simulation demonstration. We are going to generate some data from a real mean function where x1 and x2 are the active predictors and x3 and x4 are the inactives because they get multiplied by beta values of 0, so they don't become part of the mean function. The real beta values that generate the data for x1 and x2, beta 1 and beta 2, are 1 in this little simulation. Here is the R coding for generating this random data, and I guess what I want you to see down here on the bottom is the variance covariance matrix of the predictors with each other. And you'll notice that each predictor with itself has a variation that's about 1, and on the off diagonals, the covariances between these predictors are basically 0. These data were set up to be predictor data that are uncorrelated with each other. And we're going to estimate a model from this set of data, and let's look at what happens. So some randomly generated data, and you'll notice that the R software picks up the fact that x1 and x2 have coefficients that are right around their true coefficients of 1. The estimated ones are close, and those predictors x1 and x2 are significant. The data is picking up the fact that those are really part of the data generating system. x3 has a beta coefficient that's right around 0, like it is supposed to, and it's not significant. However, accidentally, x4, which is an inactive term, it isn't part of the data generating mechanism. Beta 4 is coming up to be part of the it's showing up as a significant predictor when in fact it really is not. Here's a different simulated data set where the predictors are very correlated with each other, and what you're supposed to notice here is that on the off diagonal, some of these predictors are quite correlated. So for example, x1 and x3 have a very big negative covariance. That's because they've got a negative 0.95 correlation. You will also notice that x2 and x4 have a very big positive covariance. And so there's interrelationships between the predictors. When we estimate a model based on these data, you will notice that x1 turns out to be apparently significant. It is part of the generating mean function. x2 is getting lost, even though it is part of the true data generating process. It's getting lost because it's so closely correlated with x4 that x4 appears to be taking its place as significant. X3 and X2 are looking not significant. And so the purpose of this overhead in this simulation is to show you the difficulties we have in determining active and inactive predictors when there are correlations between our predictor variables. And so it's a moment of caution. Here's what we get if we compare the compare coefficients function between the two models. You'll notice that the standard errors for the correlated predictors model are very much higher than the standard errors for the uncorrelated predictors model. And you'll notice that we get a little bit of variation in actually what the estimates are doing. So on overhead 10, notice the variances are bigger for the correlated predictor data set, and that in general we note that being able to find active and inactive predictors and terms means we're going to need more data when predictors are correlated. And also notice that if you just would decide to take the model for the variables that have big values of t, most significant ones, you sort of get a wrong model for this second simulation. You would pick predictors x1 and x4 if you just look at the p-values, and that is not the set of active terms. You'd get a wrong model. One of the issues going on here is the one of correlation between predictors, and one extreme level of correlation is called collinearity, when two predictors can be expressed as linear combinations of each other. They are said to be collinear. And whenever this would happen, if you would try to put both of these predictors into a regression model, the R output would come back and say that one of the parameters could not be estimated. And that would be a clue to you that you have predictors in your model that are functions of each other. And so that's what that would mean if you see that in your output. One of the impacts of correlation and intercorrelation, collinearity between variables is that the standard error increases. And we saw that earlier in the simulation. And the amount it increases can be quantified by a quantity called the variance inflation factor. And so if we have a simple multiple regression model like this, where the mean function is beta naught plus beta 1 x1 plus beta 2 x2, the variance of one of the parameter estimates from our output is the sigma squared from the multiple regression model error variance parameter. It is multiplied by 1 over the variation in the xj variable, predictor xj. After all, that's the beta hat we're studying. And then it's divided by this quantity 1 minus r squared 1, 2. And this 1 over 1 minus r squared 1, 2 is called the variance inflation factor. And what it measures, R1, 2, is just the correlation between the two predictors x1 and x2. How correlated are they? And so you can see that the variance inflation factor goes up a lot when the two variables would be very positively or very negatively correlated with each other. And so the definition is that the variance inflation factor is the increase in variance due to the correlation beyond what would have been obtained if the predictors were uncorrelated. And so it's a multiple of how much additional variance is being produced because of the intercorrelation. It gives you a way to identify how much variation is coming from correlation in the predictors. When you have a bigger multiple regression model with more than two predictors, this variance inflation factor expands logically to a multiple correlation Rj squared, where that is the multiple R squared for using xj as a response variable and using all the other predictors to predict it. And so it's the percentage of variation in xj that can be explained by the other predictors. So it's basically an R squared. When the other predictors can heavily explain predictor xj, we get a big inflation factor. For our two simulated data sets that we saw before, here is the variance inflation factor output. You'll notice that we basically don't have any variance inflation when the predictors are uncorrelated. There's just a little bit of randomness correlation in those predictors, and so we get a very slight inflation just from randomness. But when the predictors were constructed on purpose to be very correlated with each other, you notice we get about 15 to 16 times the variance of what we would get from uncorrelated predictors, suggesting a very serious problem with correlation in that data set. Now we move on to ways about picking and choosing active and inactive predictors. Let's first consider a subset of predictors, XC, candidate subset, subscript C for candidate. And let's suppose the particular predictor set we're thinking about happens to be all of the active predictors. What we would find in that case is that the candidate set would have predicted values and mean functions very close to what we would get from the active predictors. The idea here is that if your candidate set is really close to the set of active predictors, you're going to get a mean function and an estimated mean function that'll be really close to the truth, and it'll be really close to what you're getting from your actives. As your candidate set drifts away from the active predictors, you'll get bigger residuals, your model won't be as good, your residual sums of squares will increase when you miss information. And a way to quantify what is going on in your model and how good your model is the Akaike Information Criterion, AIC, and it's really made up of two terms. The first term is based on the residual sums of squares of your candidate model, and of course residual sums of squares being smaller is better, and of course the logarithm of something smaller is also better, so this is just smaller is better here for this first term. And the second term is involving P sub C, the number of parameters in your candidate model. Well, 2 times the number of parameters in your candidate model. And if your candidate model is bigger and has more terms in it, that second part of the AIC statistic will get bigger. That is called a complexity penalty. Your AIC statistic will get bigger if you have a bigger model and you have more parameters. It's also true that if you have a bigger model and more parameters, the residual sums of squares is going to tend to be smaller because you're using more predicting information to explain the response. So adding more stuff, more predictors to your model, tends to make this first term go down, but the second term go up. And so this is a real balancing act here between adding predictors that are good, which will make this go down a lot, and only make this go up a little bit, like by 2. And so this is a balancing act between putting in good predictors that explain the response and making this go down, and not overly penalizing yourself by adding stuff to your model. So it's a way to get an efficient, parsimonious model. In general, as it says here in the third bullet, smaller is better for AIC. Better models have smaller AICs in general. BIC is the Bayes Information Criterion, and it basically works the same way. You have a fit component in the first term and a penalty component in the second term. Other kinds of applications and other kinds of things in your statistical life may use the Bayes Information Criterion. I'm not going to talk about it further for this class, but you will see it perhaps in other contexts. Some statisticians are starting to prefer it better than AIC, but I will leave that for your future statistical life. But I want to point it out here that it's a similar measure to AIC, and I won't be talking about it again, but some believe it is superior to AIC. Another statistic which you need to be aware of works the same way basically as AIC. It's called the Mallows C statistic, and it's really formed very similarly. You have a part of the function here in the beginning that smaller is better, smaller residual sums of squares is better, and you have a penalty term over here for the number of parameters that you have, and so a C statistic which is smaller is also better, just like AIC. Very similar kind of idea. Another concept which I want you to know about, I won't use it very much in this class, but I want you to be aware of the idea because it's being used more and more in statistical work, is the idea of cross-validation, and in particular the press statistic. And I'm not really going to go through the details very much here, except the basic message is that cross-validation means break up your data set into two parts at random. A part that is used to estimate parameters, the beta hats, and another part which is to see how good it fits your data, and that's the data set called the validation set. So you use your construction set to estimate parameters, and then you use the validation set to examine the fit of your model. And there are some statistics to help you decide how good your model is. And so you will tend to want models that have small values of this press statistic. You want models that are going to have small differences between the observed data in your validation set and the predicted values. I'm not going to go through too much more of that. And now we get on to model selection, and the first main method I'm going to talk about is called forward selection. It's easy to understand, and it's a good way to start our discussion, but it isn't actually a good method to use, which I think will come across clearly in your homework problems and things. The idea here is let's start a model with an intercept beta parameter, beta not parameter only, and let's go through all the predictors that we have in our set and add to the intercept the predictor which has the most significant smallest p-value or biggest t-statistic. And that will be the first term we enter into our model. And then we will look through the remaining predictors and add the next most significant predictor and keep adding significant predictors one at a time until we run out of significant predictors to add. And that's when we stop. And that is the forward selection method. Another option is called backward elimination. And in this case, we start with everything in the model. Our candidate set is the entire predictor set. So this means we're going to start with every predictor we have, active and inactive predictors, and let's consider getting rid of one predictor at a time. And what we'll do, of course, is get rid of the predictor that has the biggest p-value, the one that seems to be the least correlated with our response. So the smallest t-statistic in absolute value. Let's get rid of that predictor. And then let's look at what's left and then get rid of the next smallest absolute value t-statistic. And let's keep getting rid of insignificant terms until we're left with only terms that are significant. That's backward elimination. And then there are options called stepwise options to either going forward or backward. Probably best to think about it in terms of going forward. As we add a new significant term to a model, what we should do really is check to see if all the predictors that were added previously are still needed in this new model. Sometimes what can happen is a predictor that has been added at stage 2 is no longer needed when we get to stage 7. All the other predictors that have been added afterwards, stages 3, 4, 5, 6, and 7, are now so effective that we don't need the predictor that was added back at stage 2. We would like to edit our choice, and that's what stepwise methods do. These commands for doing this kind of stuff, the command is called the step function, and you need a model object, and usually it is a full model, some sort of base model to start with. The scope option tells the model selection process to add terms up to a certain maximum complexity, or reduce terms until a certain minimum complexity, and that tells the model selection process how big or how small to make models. Sometimes we have a good idea that there are predictors that really need to be in a model no matter what, and for theoretical reasons or for past practice we know these things to be important and part of our model, and so we wouldn't ever let a model selection method exclude them. So that would be a way to restrict what terms are required to be in a model. And then there's the forward and backward options, and there are other options like scale equals 0 means we need to use the AIC statistic to do our choosing, and other options. You can read the R help step function will help you with the options and how to use it. Here is an example for doing forward selection. I make a base model, M0, M0, that uses the log of, I believe this is like accident rate for some highway data, as the response, and I'm going to use the log of length of roads as the only predictor, and it's from the data frame highway. And then I invoke a step function which says, okay, start with this base model and let's go direction forward, and let's let the smallest model that we will be satisfied with be the log length. I'm not willing to think about any model that wouldn't have that. And let's let the most complex model be all of these predictors, if we need it. And then let's go forward. And we get some output here on this particular screen, and it's going through one by one for adding things. You may need to go through the lecture notes and expand the magnification so that you can see this, but I'll talk about it and you can listen while you look at the expanded file. The first output we get tells you the starting AIC statistic for a model that has only log length in it. It's a negative 43.92. And then what the output shows you is what the AIC statistic would be if we add any of these terms. SLIM would give you an AIC statistic of negative 66 something. Notice that's quite a bit smaller than the AIC statistic we start with. And adding ACPT gives us an AIC statistic of negative 60, and so forth. Here are the AIC values for adding any of these additional predictors. Oh, and it even shows you what happens if you add nothing and just keep the model as it is. So what forward selection will do is it will add a term that most improves, reduces the AIC statistic, and that of course is SLIM. And that moves us to the next stage. We have a model that has log length and SLIM. The AIC statistic is the negative 66.28, and we think about adding more terms. Adding terms will change the AIC statistic, partly because we add an additional term for the penalty, but it also changes the residual sum of the squares. According to the second stage, the best variable that we could add would be ACPT, because it reduces the AIC statistic from a negative 66.28 down to a negative 68.31. And so therefore it is added. We move to stage 3 where we have 3 predictors in the model, log length, SLIM, and ACPT. We look through all the other predictors that we've specified to add, and only log of TRKS should be added because it slightly reduces the AIC statistic, and so we add that one. We move to stage 4, and our AIC statistic is negative 68.94, and it can no longer find a predictor that reduces the AIC statistic, and so the method stops. Now we're going to look at doing backward elimination. We'll make a base model M1 that has all of the predictors in it, log length, but all the rest as well. And we do a step function off of that base model. We specify that the lowest, smallest model we're willing to go to is log length. And the biggest model we're willing to have is, of course, all of these predictors. We're going to go backward elimination. And it looks like I'm changing the scale here to sigma hat M1 squared, and I believe that is going to choose things according to the CP criterion. We'll see in a minute if that's true. And this will be hard to see. You'll need to look along in the lecture note PDF and expand the view zoom so you can see this. We start off with an AIC statistic of looks like 12. It looks like the model that we're starting with has a CP statistic of 12. And we think about getting rid of terms one at a time. Getting rid of lane will have a CP statistic of about 10. And none of the others will go that small, so getting rid of lane is the first choice. We now have a base model that had all of the predictors we started with, but no lane anymore. AIC statistic 10, CP statistic is 10 at this point, and it looks for other terms to get rid of. LWID is the next one that we get rid of because it lowers the CP statistic from 10 down to 8.23. And we remove, and we remove, and we remove until we get to a point down here on the bottom where the model has log length, log ADT, log SIGS1, SLIM, ACPT, and ITG. No other terms can be removed that still reduce the CP statistic, and so this is where backward elimination will stop. Let's just take a look at a little sobering example about doing model selection. I've got some data here that have 100 observations. There's 50 predictor variables to pick from, and none of these predictor variables enter the mean function. They are all inactive. There are no active terms in this simulation. None of the predictors are related to the response. They are just totally randomly generated predictors. I want you to see what happens. Something very disturbing happens. If you build a model relating the response to these 50 predictors, you should expect an R squared of about 0.51, just from data that are just random. You can get R squared just by random accident. R squareds will tend to get inflated and tend to be quite large from just random sets. So please beware that you can have fairly big R squareds even from data that are just randomly generated. Now there's some complex simulations going on here, and I don't really expect you to understand all of this coding here on overhead 29. But basically what I'm doing is, for this randomly generated data, I am right in here, I'm saving the value of R squared. On the next line in G2, I'm keeping track of which t statistics were bigger than the square root of 2, and which, on the next line G2, which t statistics were bigger than 2 in absolute value. So I'm sort of picking through what ones gave significant results. And then on the next page, overhead 30, this is for the generated data. We get an R squared from just random predictors of 0.54. There were 11 terms that had t-statistics bigger than the square root of 2, and there were 7 predictor terms that had t-statistics bigger than 2 in absolute value. So just in a randomly generated data set, you'll get terms that look significant just from randomness. If you pick through, and overhead 31 is picking through and only keeping the predictors which were bigger than the square root of 2, you'll notice that the p-value for the overall f-test is quite small, suggesting that if you did a look at the overall global f-test, this set of just random predictors that accidentally had odd-looking t-values, it would look like this was a significant set of predictors. And the same is true on overhead 32 when we only are looking at the predictors that had t-statistics in absolute value bigger than 2. We also have a very small global f-test p-value, and this subset of predictors is going to look very significant, even though it's just randomness and we're picking out the random ones that look significant. We get an inflated sense of significance for this particular model. So please be aware that model selection is going to produce artificially more significant looking results, and that's something to be aware of. I'm not going to spend too much time on the best subsets regression here, starting on overhead 33. I just want you to be aware of some other packages and functions in R that you can sift through and look at different model subsets. And so here on overhead 34, I've used the regression subsets command from the LEAPS package to give me a list of the predictors that are involved in the 2 best models of every size. So what's going on here in the first 2 rows, these are models that only have 1 predictor in them. What are the best models? Well, the very best model is to have SLIM in the model. It's the star here. And the second best 1 predictor model is to have ACPT. The best 2 predictor model has log length and SLIM. The second best 2 predictor model has log TRKS and SLIM. And so forth for models of different sizes. This is a graphical display of how good these models are that have the different predictors. I want to talk about overhead 36, where I am plotting the CP statistic for models that have 3 predictors, models that have 4, and models that have 5. Remember that you're looking for CP statistics that are small, and so of these sizes, it looks like this 4 predictor model with these abbreviations, IL, IT, SL, I'm sorry, these are LL, that looks like I, but it's a lowercase l, little l, capital L, little lt, SL, and A is the best 4 predictor model, and you can determine what predictors those were from the abbreviation. Here is that plot in a little bit more magnified form.